When we began our research, the European Space Agency had less than a year ago released unprecedentedly accurate proper motion and parallax data that came from their Gaia satellite. So our goal was to analyze a double star system that was classified as a physical, gravitationally bound system, and use this new data to reevaluate that classification and perhaps show that these supposedly gravitationally bound stars are actually gravitationally independent. This research is important, as studying double stars helps establish the relationship between temperature, radius, and mass, and therefore can more precisely classify non-binaries based on their mass-luminosity relationship. We searched the Washington Double Star catalog using stellaroscopy, and we ended up choosing to study STF-619. We selected this system because we wanted to make our own observations, and that required the system to be visible during the time of our research. Photographing and resolving a system also meant that the primary and secondary stars needed a separation of at least 4 arc seconds, and a sufficiently small delta magnitude, which in this case meant nearly zero. STF-619 not only satisfied these constraints, but its proposed orbital solution required the secondary star to have a period of 490 centuries. It seemed unlikely that there was sufficient data to support this solution because the system had only been observed for 2 centuries.
We contributed to the historical observations of STF-619 by making our own measurements using the setup shown in the image to the left in this slide. Because we operated the telescope as opposed to a robot, we were able to ensure in real time that the images were properly focused and unsaturated. The image to the right is one of our photographs. In order to find the separation and position angle of STF-619, we analyzed 6 of our sharpest images in AstroImage J. Here's a screenshot of the photos being analyzed.
While researching STF-619, we also came across a rectilinear solution published by Scardia et al. In 2017 that included 5 parameters for each star. Scardia's prediction for the time when our measurement was taken is plotted on this graph in orange. The historical data is shown in black. The purple dot shows a prediction based on our XL trend line of the data. The primary star is at the origin. The dots show the position of the secondary star. Ephemerides, predictions of the double star's position based on an orbital solution based on Kiselev's orbital solution from 2009, is plotted on the graph in blue. This prediction is quite different from the point predicted by Scardia's linear solution. The green point is our measurement, which is calculated to be 0.26 arcseconds away from Scardia's linear solution and only 0.19 arcseconds away from the ephemerides. However, Scardia's prediction is significantly closer to the linear trend line we found of the data using Microsoft Excel.
We also analyzed the proper motions of the stars in STF-619. Proper motion, or PM, is the movement of a star across the night sky over the course of a year. A way of quantifying the difference in 2 stars' proper motions is through calculating the PM ratio. If they are close to each other in the sky, and the PM ratio is less than 0.2, the stars are likely gravitationally bound, but if the PM ratio is greater than 0.6, they are probably gravitationally independent. Based on data from the Gaia Data Release 2, we found the PM ratio to be 0.59. Thus, the stars are likely gravitationally independent. However, we need more evidence to confirm this. The diagram on the right is a graph of the PM vectors we obtained from Gaia DR2. Furthermore, we analyzed the parallaxes of the primary and secondary stars. By substituting the data provided by the Gaia Data Release 2 into the parallax equation, we were able to find the range of possible distances between Earth and each star. As this table shows, the minimum distance between the 2 stars is 35.4 light years, which strongly suggests that they are gravitationally independent.
We ultimately concluded that STF-619 is probably an optical double. However, we tried to make it clear that there is still a lot of uncertainty. Although our measurement fits the ephemerides more closely than the rectilinear solution, the linear prediction better fits the trend line of the historical observations. Meanwhile, the proper motion data is ambiguous, although it does tend toward confirming our conclusion. The parallax data is likewise suggests that STF-619 is an optical double. If STF-619 continues to be observed over the coming century, it should become clear with a high degree of certainty whether these stars are gravitationally bound.